say with Benko. So Alexei, give a talk, please.
Thank you for the introduction. My name is Alexei, and I will give a talk about ARX differential probabilities. This is a joint work with Alex and Baptiste. First, I will give a brief introduction to rotational XOR cryptanalysis, then introduce our main contribution, which is the exact probability formula for all rotations, and then I will discuss some interesting applications. Rotational cryptanalysis was introduced by Kovaratowicz and Nikolic at FSE 2010. And the idea is when you're taking some symmetric key primitive to query encryption of some input, and at the same time to query encryption of the rotation of the input, where rotation is done for every word of the input bitwise for a fixed amount of bits. And then the hope is that at least with a decent probability, you will get rotation of the original output and thus get a distinguisher of the cipher. Rotation propagates nicely through the XOR operation. And if you have XOR with the key, then you have to rotate the key, which means that for keyed primitives, we have to work in the related key setting. For modular addition, which is the main target of this technique, the ARX primitives, the rotation propagates with some probability, which depends on the amount of bits that we rotate. And it ranges from 1/4 to 3/8. The main problem for rotation cryptanalysis is that for a XOR with a constant, it doesn't always work in the way we would expect. And the idea that was already given in this 2010 paper was to study how far are we from the result that we would want and the actual result. And this was explored more in the work of Ashur and Yu at FSE 2016, which introduced rotational XOR cryptanalysis, or short ARX cryptanalysis, where in addition to rotations, we also allowed to introduce differences to the state. And this really becomes like a differential cryptanalysis, where we have to choose some input difference, some output difference, and study the propagation of differences, search for good trails, where just the propagation rules are slightly different from normal differential cryptanalysis. And specifically, the main tricky part is propagation through modular addition, where the Ashur and Liu proposed a formula how to compute the probability given the 2 input and 1 output difference. But their formula was only proposed for the case of rotation by 1 bit. So for rotation from all bits, this was not proposed. And in this formula, you can see mainly two disjoint cases. And in each case, there is this brown term, which corresponds to usual differential probability through modular addition. And there is some extra coefficient in each of the two cases. And here we need to compute the XOR of the differences and the so-called not all equal vector, which is equal to 0 at some position if the 3 differences agree. So if they're all equal to 0 or equal to 1, and otherwise this bit is equal to 1. So our main motivation was to extend this work to a high amount of bits, so for rotation for any k, more than 1. And our main result is a compact formula, which I will describe later in details, of computing the probability of propagation of differences through modular addition in the rotational cryptanalysis. And one immediate observation we had was that previous formula, even for the case of k equals 1, is not totally correct. There is a small class of transitions where the actual probability is 50% lower or higher compared to what was given by the previous formula. In addition, there was a recent work by Huang et al. From Oxford Computer Journal, which tried to tackle the case for rotation by any number of bits, but it also has problems. It has large discrepancies with experiments, which was also given in their paper already. And there are some issues with precision of condition for validity of trails. We also resolve this problem and provide a nice condition for verifying whether the trail is valid or not. I will describe it in details later. And of course, since we wanted to avoid any more mistakes in future, we extensively verified our theorems by comparing against exhaustive computations of probabilities, but also against other methods based on finite state machines. And so now we are sure that these are correct and can be used for any future rotational XOR cryptanalysis. So now I'll go into more details of our formula. To compute it, we need to consider our three differences and split them into two chunks each. One chunk of k least significant bits, where k is the amount of rotation that we do, and one chunk of n minus k most significant bits. Then our claim is that the probability of ARX differential transition through model addition is given as a product of two terms, where each term depends on the three corresponding chunks, but also on the least significant bit of the other chunks, namely on the XOR of the least significant bit of the other chunks. And this creates dependency between these two parts of differences, which made the difference to find the formula, but also to prove. Right? A large part of our work is devoted to proving the result. And the terms have the following expression. So the main term is 2 to the minus d, where d is the weight of this not all equal vector corresponding to these chunks. But what's more interesting is that there is a correction factor, which happens only when the differences XOR to all zeros or all ones. Right? So in these special cases, we need to add extra correction, which evaluates to 2 to the minus m, where m is the size of the chunk, which is k or n minus k. And the sign of the correction depends on this least significant bit of the other chunks. This theorem only applies when the probability is non-zero. So when we know for sure that the trail is valid. And to compute this, we describe a simple condition, which requires to compute two vectors. So vector u, which is essentially the XOR of the differences and of the neighbor bits. And the vector v was, as before, the not all equal vector. And for x differential to be valid, we need that all coordinates of u are less than or equal to the respective coordinates of v, except two positions, I equals 0 and I equals k. And this might remind you the condition for normal differentials through model addition, which were given already in 2002 by Lippmann and Moriai, where the condition is essentially the same, but all bits have to be checked. While in our case, we have to skip checks for position 0 and position k. And I would like to briefly mention the impact of correction of the previous formula from 2016 for the case k equals 1. And we show that it is actually correct unless we have this correction factor for the big chunk of the differences, namely that the differences don't sum to 0 or don't sum to all ones, where we exclude the least significant bit. And while the correction factor can be quite large, so twice lower probability or twice higher probability, in practice, it's unlikely to happen, because for high probability trails, which we often have in our search, the correction would be negligible, because this factor 2 to the minus m would be small compared to the actual probability. And in low probability trails, we would have dense differences, and it is unlikely that we will have this condition to happen. So our conclusion is that concrete trails from the results are probably not affected by this small error, but there were many works which used this previous formula and claimed a search for optimal trails for various primitives. And these claims need to be revisited to make sure that they didn't miss better trails when using the correct formula. Now I will describe some modeling and applications of our technique. We propose two MLP models to search for trails using our formula. One is heuristic and is based on ignoring these correction factors and just computing the weight of these not all equal vectors, which often are the main parts. And this is essentially very similar to standard differential transitions in ARX, where we only have to ignore 2 bits in the weight vectors. And in particular, we propose a model, MLP model, for a variable that is equal to 1 if and only if a set of other chosen variables are all equal together. So if they are all equal to 0 or all equal to 1. And interestingly, this can be achieved only with 4 inequalities, independently of the number of variables. We need this for computing the number of not equal bits, but also to finding when we need this correction or not in the formula. And the second model is precise to model exact expression from our result, which we implement using piecewise linear constraints, which are available, for example, in Gorobi, which are essentially sort of lookup tables that allow us to model logarithm computation to mix this multiplicative relations between probabilities and also additive relation of these corrections. And the way we applied our models was first applying heuristic model to find a heuristically good solution, and then using it as a starting solution to the second model and trying to optimize it further to get a good trail for the full correct expression for the probability. And here I would like to present results for ALZ, which is a 64-bit ARX box, which essentially consists of 4 rounds of modular additions, 32-bit modular additions. And there are 8 instances for ALZ, 1 per each row of this table, which differ only in the constants that are used in the permutation. And in the first column, you can see the result of applying the automatic framework Cascada, which implements the search with the previous formula for k equals 1, and it finds optimal trails with respect to this previous formula. Then we implemented our model, again for k equals 1, to compare with previous results. And we, in all cases, we found the same trails. But in our case, we could not prove that they're optimal, except in the case of the constant C5, where our trail is slightly worse, but probably it could be improved by letting the solver to run for more time. In third column, we describe the more interesting, the key focus of our work, ARX differential trails for rotations bigger than 1, using our formula. And here we can notice that for many constants, these trails, they are much better than ARX differential trails for rotation equal to 1. So this means it's useful to study rotations bigger than 1 and search for best trails there. For example, for the constant C3, our trail is 64 times better in terms of probability than the best trail for k equals 1. And in the last 2 columns, you can see reported results from the other paper I mentioned, which are not precise, but also not competitive with these works. Another interesting contribution I would like to mention is MILZ, which is a proof of concept backdoor, where we chose maliciously constants to ensure that we have a good RX differential trail, but no good differential or linear trails. And the structure is essentially the ALZ permutation, iterated in total having 12 rounds. And the only thing we changed is we applied the XOR with the constant to the full state, and we changed the constants every round. And we found a maliciously chosen set of constants for which there is ARX differential. And these are only lower bounds. We don't know the best trails for LZ. And we also propose a more aggressive variant where the constants are less random looking, but the probability is improved to the minus 25. So for conclusions, for the theory part, we propose the compact formula for computing exact probability for all rotations, which corrects some previous errors, but also makes it possible to search for rotations bigger than one. There is also some useful theory for general RX differentials in the paper. One open problem I would like to mention is that our formula is not applicable to model addition with a constant. And for there, we could not find compact expression, and we had to use standard techniques based on state machines to find the probability. So interesting open question is whether it can be simplified. And for the applications, our model did not always have good performance. So almost never we managed to solve the models to optimality. So we had good trails, but could not see if they're optimal or not. So I think there is big room for improvement. For example, trying to use SMT solvers instead of MLP, because some previous works on RX differentials reported good results on using SMT solvers instead. So thank you for your interest, and I'll be happy to answer your questions.
Okay, thank you very much for this talk. So from audience, do you have any questions? Okay, so we have two.
So the original kind of rotational cryptanalysis had some problems with independence assumptions, where if you had a chain of multiple additions, then the probability would be lower than just the product of the probabilities. And I think you still have independence assumptions here, but you like theoretically verified some of your results. Do you have any insights in why these independence assumptions do not have a big impact here?
Thanks for the question. Yeah, it is true. We in our search for trails, we compute the probability of a trail just as a product of probabilities for rounds. And when you talk about distinguisher, we have to see whether it holds or not. And in some cases, it can have a significant impact. And we verify this experimentally for some cases. For some cases, we observed bigger probability. For some cases, there was a lower probability. So, but we did not study in details this aspect from theoretical viewpoint. So our focus was on single model addition and using standard trail theory.
Okay, so yeah.
Is there a way? It's perfect. Is there a way to check that the constants that we put in LZ are not evil? Or is there a way to convince people that we are nice?
Yeah, that's a good question. Well, these constants might look somewhat random, but there are the patterns there. But it becomes obvious when you sort the constants with their rotations to see what difference they introduce to rotational trail. So from that viewpoint, it would be easier to detect what happens. But in general, what one would have to search for trails or to prove that there are no high probability trails for a cipher.
Okay, so do you have any question? Nothing? Okay, so thank you very much for